This video will cover graphing logarithms without the aid of a calculator. So let's first look at a super basic logarithm. Let's say we want to graph f of x equals log base 2 of x. And then we'll start adding some transformations, and I'll tell you what you need to do to make those adjustments. But what we're going to do is leverage the fact that logarithms are the inverses of exponentials, knowing that exponentials are easier to evaluate, in which case I'm going to generate a table of coordinates with that inverse exponential, and knowing that we can find inverse coordinates by just switching the x and y values. That'll get us our table for the logarithm that we can plot. So the question is, well, what is the inverse exponential to this logarithm? So we're going to say y equals log base 2 of x. We're going to say x equals log base 2 of y. And then we're going to make our exponential and logarithmic conversion that we discussed in a previous video. So base 2, because it should match the base of the logarithm, we know logs equal exponents. So we have y equals 2 to the x. That's our inverse. So we're going to make a table for that exponential. So this is the table for 2 to the x, and we'll make a note of that. Knowing that the exponential has a domain of all real numbers, and it's much easier to evaluate, it makes it an easier process to figure out what should we be picking for our x values, right? Because if we had a logarithm, it's like, well, which ones do I pick, knowing that the domain is constrained and it's not all real numbers. But now we're just going to evaluate. So 2 to the negative 2 is the same thing as 1/2 squared, so we're going to get 1/4. 2 to the negative 1 is the same thing as 1/2 to the power of 1. Anything to the 0 is 1, 2, and 4. So this is our table for the exponential. And knowing that the logarithm is the inverse to that, we're now going to get a table for this. And all we have to do is switch the x and y coordinates. So that is why we did all that stuff with inverses before and conversions in prior videos. So we can get to this point. Now we have our logarithm table. We could plot these points. By the way, we know this is logarithmic growth, and the exponential is exponential growth. So we should have an idea of what this logarithm is going to look like, because we know the exponential growth with base 2 is going to look like that, because there's no transformations done to it, so I don't think it looks like anything else. And now let's plot this logarithm. So we're going to make some points on our coordinate plane. So we have 1/2 negative 2. Sorry, 1/4 negative 2. Something maybe in this area. Then we have 1/2 negative 1, so we'll put 1 there. We have 1, 0. We have 2, 1. And we have 4, 2. And again, we know there's a vertical asymptote at 0, and I know it's still at 0 because there was no horizontal translation. So I want to be careful when I'm graphing this thing that I don't cross over that vertical asymptote and I don't touch it. So we want to stay pretty close to it, and then pass through these points and make sure this thing looks like it's increasing, right? I don't want it to flatten out or start bending down, so I don't want it to come like this, or I don't want it to flatten out into a perfectly constant function, imagining if there was, because there's no horizontal asymptote there, right? This thing's actually increasing as we go, and it's spanning a domain of 0 to infinity. So there's our graph. So we got our points for our graph by using the fact that we know exponentials are inverses, generating a table, because it's much easier to generate a table for an exponential because of the fact that we know domain is all real numbers, so we can pick what we want. We can get some negatives, 0, and positives to get an idea of the full picture, and it's also much easier to evaluate. Now, what if we incorporate some transformations? So let's make a minor adjustment to this original function. Let's say we do shift it left, say 2 units. So it looks something like that. Now it's worthwhile but to identify what transformations are actually happening, and then knowing that we're going to be working with tables. If you want to make a note, this thing's going left too. The key here is, although we identify the transformation from the function, because we're actually going to ultimately implement the transformation to a set of coordinates, We want to make sure we do that correctly. So to move a set of points left 2, we must subtract 2 from just x. Remember, x dictates horizontal movement. If I also subtract the 2 from y, that would move it down. So we don't want that to happen. So we're just going to subtract 2 from x. So we can make a note of that. Now, how we go from there is once you've identified the transformation, to get started, you're going to strip away all the transformations so that you get the parent logarithm. So remove all transformations, get the parent logarithm, then identify the inverse exponential to the parent logarithm. Okay, so this is our inverse exponential. It's just easier to do this way because we don't have the algebra tools to find the inverse of the original logarithm. Okay, so we don't have that tool set, so we have to work with the parent logarithm. Then make the table for the exponential, find the table for the parent log, and then the additional step when we have transformations is now we're going to make the table for our transformed logarithm. So to do that, we already discussed how to incorporate that transformation. We're going to subtract 2 from all the x's. So 1/4 minus 2 is the same thing as over 8/4. So I get those common denominators. We're going to have negative 7/4. By the way, the y values are untouched because there's no vertical transformation occurring here. So the only thing I'm altering are these x values. So then we have 1/2 minus 2, which is the same thing as 4/2. And you get negative 3/2. Then 1 minus 2 is negative 1, 2 minus 2 is 0, and 4 minus 2 is 2. And now if we plot this, I should have coordinates to where I can see them to plot them. But we're going to draw some points here. What we want to maybe mark off first, if this helps, I would highly recommend it so you don't make this mistake of crossing over. The vertical asymptote, again, starts at 0. We know that. And the only way it moves is if left or right shift, and that happened. So it goes from 0 to negative 2. It shifted left with the function. So we may want to just put a dotted line in here indicating that there's a vertical asymptote there, and I'm not going to cross over that thing. So then let's start plotting some points. So we had negative 7/4, negative 2. So that's just before that vertical asymptote and then down 2 units. So somewhere right there. Then negative 3/2, negative 1. So negative 1.5, negative 1. We have negative 1, 0. We have 0, 1. And then we have 2, 2. And if we graph these, knowing what our original log base 2 looked like, we can see that there's a clear shift left 2 units here. So that's the idea. Let's summarize the approach to graphing a logarithm without a calculator. So the steps, and then we'll look at one that has multiple transformations. Number 1, identify the transformations. And an optional step off of this is note how to apply to coordinates. So we're looking at a function, identifying the transformations, but ultimately we have to apply them to coordinates, not a function. So it's important to be cognizant of that fact. So once we identify the transformations, strip away the transformations and identify the parent logarithm. Step 3, find the inverse logarithm to the parent function. Or find the inverse exponential, sorry. Then generate a table for that exponential. By the way, step 1, identifying the transformations, if there are any. If If there aren't, you're already dealing with a parent log, and you can just go right to step 2. So generate a table for the exponentials, and then generate the table for the parent log by just swapping the x and y coordinates. Then 6, once you have them swapped, apply the transformations in the correct order to find the final table result. So then apply the transformations in correct order to find points for original logarithm. And then obviously once you have the points, graph. And we'll say when you graph, just be aware of the vertical asymptote, okay? So make sure you know where that thing is so you're not crossing over it. And it helps you identify domain as well. So now that we have those steps, let's look at an actual example that incorporates multiple transformations. So we did this one in class. So let's say we have f of x. We'll change the numbers around a little bit. Let's say we have -3 log base 1/2 x plus, or we'll do minus 1. We'll do something like this. Now when it comes to identifying transformations, my intention is not to trick you on this, but I want to make note of how the order in which transformations are applied. So it doesn't matter if we incorporate the horizontal or the vertical first, because one deals with x's, the other deals with y. So one wouldn't affect the other. But when it comes to if we have multiple vertical or multiple horizontal, you're going to want to know which one to do first because of the following reason. If I move, say, up 1 and then reflect, or let's say I move up 2, I have some point here at 1, 2. If I move it up 2, and then reflect it over the x-axis, I end up with a y value at -4. So I would end up down here. But if I first reflected it over the over the x-axis, reflected it over the x, not the y like I originally said, and then move it up 2, we'll end up in a completely different location. So I ended up here the second time and here the first time. So the order in which the transformation is applied matters when there's multiple vertical or multiple horizontal. And the order that they follow is vertical transformations. The order of application follows the order of operations. So vertical transformations, application follows the order of operations, which you probably know as PEMDAS. Now the horizontal transformations, their application follows the opposite of the order of operations. Meaning transformations that occur via subtraction and addition will be applied before transformations that occur from multiplication or division. So for instance, if we have a horizontal transformation, like say we identify this in our quadratic, we can see that we have two horizontal transformations here. We have the -1 and the 3. Following order of operations, what would happen is this -1 would be implemented before the multiplication by 3. So this thing would shift right 1 and then be horizontally compressed by 1/3 and not the other way around. And that's important to recognize because you would end up in a different place if the application were different. And because we're applying these on our own to generate a set of coordinates, we just want to be aware of the order. Now, if we have two things that happen because of multiplication, like reflections and stretches and compressions, well, then it doesn't really matter which one, right? Because we can just say, well, we're going to multiply by -3. That's the same thing as multiplying by -1 and then by 3, or the other way around. Now, again, I'm not going to try to trick you with this, but I want to note that in this video in case this does pop up at a later time. You know how vertical and horizontal transformations are applied when there are multiple. So now we have this. So let's graph this thing. First thing we're going to do, let's identify the transformations. So the vertical transformations, we have reflect over the x-axis, and that's identified by me multiplying this original parent function. First of all, the parent function we can identify right off the bat if we want. Log base 1/2 of x, if that helps you identify what transformations are being performed. So that's if I stripped away the -1 and the -3, that's what I would be left with. So we can see that we're multiplying that entire logarithm by -1 and by 3. So those are our vertical transformations, right? When we affect the entire function, because the function represents y, vertical dictated by y. So reflect over x is 1, and then multiplying by 3 is going to be vertical stretch by 3. So those are those two transformations. Now when it comes to the horizontal is going to be applied just to the input variable. And the horizontal transformations are opposite of what we would intuitively think as a reminder. So we can see in here that the -1 is solely applied to the x, as opposed to if I had the parent function I saw -1 like that, that would be -1 from the entire logarithm. So that -1 would be a vertical, meaning down 1, but this, the parentheses indicate it's only applied to x. So I know it's horizontal, and in this case, opposite of what I think, so it's going right 1. Now when it comes to application to the coordinates, if we want to make a note, reflect over x, we're going to multiply y by -1, right? Because we want to affect things vertically. Vertical stretch by 3, multiply y by 3. Right 1, we're going to add 1 to x. Okay, so we have the applications in parentheses that we would do for a coordinate, which is ultimately what we'll need to do to finish off this graph. So let's get started. We know the parent function that we're going to use to generate our exponential is log base 1/2 x. So the exponential is y equals 1/2 to the x. To get our table 1/2 to the x, xy, let's choose some points that are easy to evaluate. Couple negatives, 0, couple positives to get the full picture. So we're not leaving any pieces of the exponential out, which ultimately, through reflection, will prevent us from leaving out any pieces of the logarithm. So 1/2 to the -2 is the same thing as 2 to the +2, which is 4. 2, 1, 1/2, 1/4. Now we'll flip this thing over to get log base 1/2 of x. So don't forget to actually perform this inverse, because again, ultimately we want to graph a logarithm. We don't want to graph an exponential. So forgetting to flip this over, we're going to get the wrong image. Then apply the transformations. So there's only one horizontal to apply, and the two verticals that we're applying, we don't have to worry about the order because they're both multiplication. So when it comes to worrying about that PEMDAS thing, they're both the same operation. So we can just apply them actually both at the same time. So let's move the x's right 1 by adding 1. So we're going to get 5, 3, 2, and then 1 plus, so 3/2 and 5/2. And then multiply the y's by -1 and then by 3. So we can just multiply them all by -3. We'll get 6, 3, 0, -3, -6. And there is the final list of coordinates we would do for the log that has multiple transformations. So it's the same idea, we just have to apply more transformations to the final parent logarithm table. So we take that table and we start applying. But what I want you to take away from this is identifying the transformations is important so that you know how to implement them into the table. And don't forget that ultimately what you're doing is applying the transformations to coordinates, not to a function. So we identify through a function, but apply to coordinates. Plot those points, and then we will graph from there. And last, I'm not going to draw the picture of the graph. I'll leave that to you. But vertical asymptote, where is it? The only thing that affects it is moving horizontally via translation. So there's only one thing doing that here, It starts at 0. We shifted right 1. So now it's at x equals 1. This part here, that -3, has 0 impact on the location. So just know the only thing that affects it is left or right shift. That happened. So we know we have a vertical asymptote now moved over to x equals 0. And again, why is that important? That'll dictate things like domain values that you want to be aware of, and just to make sure your image is accurate when graphing without a calculator. So there is your video on how to graph logarithms without the aid of a calculator.